So this is a tutorial video for the Heat Transfer Assignment 2 by Louisefarrell. So we're just starting off with the problem statement, which says that a water pipeline is to be laid in soil underground, and the mean temperature during the cold season is 5 degrees Celsius, and the maximum temperature goes down to -5 degrees Celsius and exists for a maximum of 48 hours. Design a pipeline that can do this while avoiding ice to form, while also optimizing for pipe depth, underground, and thickness. So here are just a few constants that we are given as part of the question, and also the assumption that the length of the pipe is 10 meters, and this is the length that we will be using when we are in our calculations. So first we have to calculate the Fourier modulus, or the Fourier number. So this is the dimensionless number in which it describes the time of diffusion over a certain length L. And the formula for this, as you can see there, is F0 is equal to alpha T over L squared. Now the alpha in question is the thermal diffusivity, and this can be calculated from the values that were given in the question. So alpha is equal to K over rho Cp, and as you can see there, it is 1.591 by 10 to the minus 7 meters squared per second. And now from this, we just need to calculate the time in seconds, as the Fourier number is in seconds. So this is just the 48 hours by 3,600 seconds, which is 172,800 seconds. Now we can calculate this dimensionless number, and it is seen to be 0.027 with the assumed length of 1 meter. The dimensionless distance is also needed for the Heisler charts, and this is to do with the length and the depth. So it is the depth over the length, and it is found for 0.2, 0.4, 0.6, 0.8 and 1 meter in depth, so that we can see which depth is the best for this pipe. Now finally, what we need to look at the Heisler charts is the Biot number. So the Biot number is a dimensionless quantity which provides a ratio of thermal resistances inside and outside of a body, and it is used for heat transfer calculations. So you can see there that it's HL over K, and we already have all of these quantities, so we can find that it is 7.25 and it has no units as it's a dimensionless quantity. We also need to find the inverse of this to use for the Heisler charts. So the inverse of the Biot number then is 0.138. You can just see the figure there shows the Heisler charts, and this is how we're able to find the dimensionless temperature. This was performed for all of the depths chosen, but a depth of 1 meter was just shown there. So as you can see, the inverse Biot number is 0.132, the Fourier modulus is 0.027, and the dimensionless distance is 1, which gives a temperature reading of approximately 0.35. And just to find temperature off the value that we read off the Heisler chart, so we're using the equation there, Txt minus T infinity over T0 minus T infinity is equal to the dimensionless temperature. So we have our T infinity is -5 degrees, which is the lowest temperature, and our T0 is just the value of temperature for the soil, and that's just assumed to be a value of -3 degrees, as the soil would be a little bit warmer than the air. So we're now finding Txt, and we're using the example that we used for the Heisler chart, where the value of x over L is equal to 1. This is performed for other values of x over L, but this is just an example. So we rearrange the equation and we get a value of Txt to be -4.3 degrees Celsius. So just going through some other elements of the pipe design, the PEX pipe was the material that was chosen. It's more flexible than the traditional PVC pipe, so it performs a bit better under the hot and cold conditions. The PEX pipe is a multi-layer PVC pipe that can bend up to 90 degrees. It's more expensive, but it's less susceptible to corrosion, so it would last longer. And PEX and PVC are both really flexible, which would mean they would perform under hotter and colder conditions than traditional metal piping. Now we're just going to calculate the area of the pipe. So this pipe has an outside diameter of 26.67 millimeters And this corresponds to the pipe being 3/4 of an inch in nominal diameter, and this is typical of this pipe. The thickness is 4 millimeters, and the inside diameter is the outside diameter minus 2 times the thickness, which corresponds to an inside diameter of 18.67 millimeters. The area is pi d squared L over 4, which is 273 millimeters squared, which equals to 0.000273 meters squared. So we can now calculate the heat flux, and this is calculated from the mass transfer coefficient multiplied by the specific heat capacity and the change in temperature, but it's also found from the heat transfer coefficient multiplied by the change in temperature. We can get this heat transfer coefficient from the equation there, and it's seen to be 3.0818. For x over L is equal to 1, so this is a depth of 0. Our temperature that we found from the Heisler charts was 7.5 degrees Celsius, and then our final temperature is minus 5 degrees Celsius. So our heat flux is 7.7045 joules per meter squared per second. Now, using the heat flux, we can find the final temperature of the water to ensure that it's not freezing. We need to use the mass transfer rate, which can be found by multiplying the density by the area by the velocity of the water. Now, a velocity of 0.008 meters per second was used for this. That was just an assumption. So the mass transfer rate was found to be 0.00218 kilograms per second. Now that we know the mass transfer rate, the heat flux, and the specific heat capacity, we can find the final temperature of the water, which is found to be minus 4.31 degrees Celsius, which is obviously too low as water freezes at 0 degrees, so we need to use a different depth. Values ranging from 0 to 1 meter were all used, but it was found that a value of 0 meters gave a final temperature of 0.5 degrees Celsius, which is satisfactory. This is the optimum depth of the pipe. Thanks so much for watching, and I hope you learned something new.